All right, here we go. So this is going to be kind of a weird video, right? So we're going to be learning about work and rotational kinetic energy. Honestly, most of this is stuff that we learned when we did linear motion. We're just going to have slightly different notation for stuff because we're going to have different symbols. So we're going to hit a lot of information. There aren't going to be a ton of examples. And I'll try to kind of provide you with some problem-solving strategies. And then I think really the best way for you guys to tackle this is to just kind of dive into the problems and kind of see what you can get done, all right? And obviously, as always, we'll talk, yeah? All right, so here we go. At this point, we've now learned how to calculate the rotational kinetic energy. And we know that torque produces angular acceleration, which changes that rotational kinetic energy. But what's the connection, all right? Well, so here's what I'm saying. So we had earlier in the year learned that assuming that everything is linear, you can calculate the work done by a force by simply multiplying your force by your displacement, right? And if the force and the displacement aren't parallel, then you got to deal with components and stuff. Okay. And so we can do some algebra. We can use a jumper equation and replace delta x with delta theta times r. We can regroup our parentheses. And we discover that work can also be calculated by multiplying torque by change in theta, okay? And so the idea is if a torque is applied to an object and that causes the object to undergo some change in angular position, then work is done, all right? So this is what I'm saying. So pretty much all of our old equations that we learned when we did work and energy, we're going to redo those same equations with their angular counterparts, okay? So what was previously work equals force times displacement, now when we're talking about angular motion, well, the angular counterpart to force is torque, angular counterpart to displacement is angular displacement, all right? And so that's all this whole section is. It's just replacing linear values with angular values, all right? So using kind of that same logic, if your force is not constant, then you can't just multiply, right? You got to take an integral, right? And so one of the things we learned was that the integral of force with respect to position gives you work, all right? So now, talking angularly, if you integrate torque with respect to angular position, that also gives you work, okay? The opposite of that then, like the opposite of taking the integral would be taking a derivative. So it turns out that force is the derivative of work with respect to position. And so torque is the derivative of work with respect to angular position, okay? We had previously learned the work kinetic energy theorem, right? That the net work is equal to the change in kinetic energy. Well, similarly, the net work done by torques is equal to the change in rotational kinetic energy. I guess I should write that. Let's see. The work done net by torques is equal to the change in rotational kinetic energy. Okay? And this really still works. Well, yeah, I'm getting ahead of myself. All right, cool. Let's see. So what else? So we had learned that power is the rate at which work is done, but that you could calculate instantaneous power by taking the dot product of your force and your velocity, right? And again, if there's no angles, that just means multiplying, all right? So now the angular counterpart to that becomes power is the rate at which work is done, which then just means torque times angular velocity, right? Because the angular counterpart to force is torque, angular counterpart to velocity is angular velocity, okay? So really this whole section is just going to be about familiarizing yourself with those equations, all right? So like I said, I'm not going to give you any examples, but I'm going to kind of talk you through sort of what to expect, all right? So in the past, we had learned so let's do this. So linear, and then maybe over here in red, oh shoot, we'll do blue, I guess. We'll do angular, right? So in the past, I might have given you a problem that said this. The force acting on a particle at position x is whatever, 3x squared plus 2. And then I might say, how much did the energy change? Or how much work was done between these 2 points, right? And then you'd go, oh, well, the work being done is the integral of my force between my 2 positions. So maybe the positions are whatever, 1 and 4, right? Okay, so angularly it becomes the exact same thing. So the idea is I might give you an expression for the torque as a function of theta, you know, and maybe it's 3 theta squared plus 2, right? Oh, now we can calculate the work by taking the integral between my starting position and my ending position. Okay, so it's literally the same thing. All we're doing is we're replacing each of our linear quantities that we learned about a couple chapters ago with angular quantities, all right? What about graphs? Well, linearly, I might give you a graph that looks like this, force as a function of position, right? We can find the area, and that area would tell us how much work was done, right? Okay, and don't forget, too, you can always relate that work to some sort of change in energy, right? For, you know, I guess for the purposes of this chapter, because we're talking angular, we're going to be talking about change in rotational kinetic energy, usually. So let's see. So over here, then, our graph would be this. We have a torque versus theta graph, right? You find your area, and that area would give you your work, which, as I just said, would be your change in rotational kinetic energy. Okay? All right, let's see. What's next? All right, so those are your 2 integral options. In terms of derivatives, what's that going to look like? Well, you know, maybe I give you a thing that says, you know, an object's kinetic energy as a function of position is, you know, whatever, 2x cubed plus 3, right? And then I want to know how much force, what your net force is, right? So then you go, oh, well, let's see. Net force is the derivative of net work with respect to position. Change in net work is the same as change in kinetic energy. And so just take your derivative, right? So you get, what's it, 6x squared, right? And so the angular counterpart would be the same thing. Maybe I'll give you an equation for the rotational kinetic energy as a function of position. 2 theta cubed plus 3. And then I'll tell you, oh, the net torque acting on this thing is, oh, sorry, no, I'll ask you to find the net torque. And so the net torque would be, oh, well, that's the derivative of the net work with respect to position, right? And then just take your derivative. Let's see, that's the derivative of your RKE with respect to position, and then take your derivative, and you get 6 theta squared, okay? Oh my gosh, I put my things too close together. What are we going to do? All right, graphs. Let's see, so we learned that if you've got a work versus position graph or a kinetic energy versus position graph, then the slope is your net force, right? So angularly, if I give you a graph that is work or rotational kinetic energy as a function of position, then your slope is your net torque. Cool? Oh, cool, we can make up some room here. Power is force times velocity. So if you know the force and you know the velocity at a given point, you can find your instantaneous velocity. It's not much to do here, right? Like, oh, I know that my object is, you know, acted on by a force of whatever, 300 newtons. And at that instant, it's moving at 2 meters per second squared. So that's 600 watts, right? So the angular counterpart would be similar. You can just say, oh, I know how much torque is acting on my object at a given instant. I know the angular velocity at that given instant. So I'm just going to multiply. Okay? Derivative of work, dt. So we learned that power is the rate at which work is being done. That doesn't change at all, right? Power is the rate at which work is being done. I guess maybe this would be maybe the change. For linear motion, work is usually thought of as your change in kinetic energy, right? If you're talking net force. And so over here, this would be your change in RKE per unit time. So, you know, basically your homework is just going to be, you know, trying problems and familiarizing yourself with these angular problems. All right, we are almost done here. Let's see. graph of work versus time, right? So maybe I'll give you an equation that's work or kinetic energy versus time. The slope is your power. Okay, over here for angular, exact same thing. You're going to have work or rotational kinetic energy versus time. Once again, your slope is your power, right? Because the power is the rate at which work is done with respect to time. All right. And then finally, let's see, we can work backwards. The derivative of work with respect to time, the derivative of work with respect to time is power. So the integral of power with respect to time is work. So work is the integral of power with respect to time, right? So I might give you, maybe I'll give you an equation that's the power generated by such and such a force is, 4t cubed plus 5, right? And then I'll say how much work is done between these two times. So you're going to go, oh, well, work is the integral of 4t cubed plus 5 between my starting time and my ending time. And this is all with respect to time, right? And so I guess the only thing to remember there is that your work, once again, could be your change in kinetic energy. For angular, it's all exactly the same, except this becomes change in rotational kinetic energy, right? Okay. So that is number 8. And then finally, oh no, this last one with your graphs. So if I give you a graph of power versus time, well, the integral of power versus time is work, so that means my area is work. Okay, and that work is going to either equal your change in KE for linear or your change in RKE for angular. Okay, so I know there's a lot here, and this is probably overwhelming, and you're maybe a little bit frustrated with this video. Most of the problems in this section are going to be very, very simple. It's simple in the sense that, when we did this with linear motion, the problems got really complicated, right? Where there were a whole bunch of steps, and maybe there were weird angles, and you had to do systems of equations. The problems for this section are going to be pretty straightforward. They're basically going to be one-step problems. Do you understand the angular counterpart to this linear equation? And that's it, okay? So to run through an example of each of these would take forever. I think, like I say, I think you're better to just try the problems, and then we'll troubleshoot on the back end and see which ones gave you trouble, okay? So, I think it's funny when I ask you guys questions, like you're going to respond. It's a video, Mr. Hecker. Okay, cool. There we go. Have a good day.